we have a heuristic search procedure that is called the AO star algorithm that we will look at here. So, the AO star uses a heuristic function. It estimates the cost of an optimal solution from a node n to a set of terminal nodes, and each node is somehow connected to its successor. It remembers where it came from. Each node will have an associated age value that serves as a measure of goodness of the node. Rather than the two lists that we have used while we were doing A star, the open and the close list, the AO star algorithm uses a single structure, a graph, that represents part of the search graph that has been explicitly generated so far. Two major operations are involved in this algorithm. One is the top down graph growing, where we get to the partial solutions, and then there is another which is the bottom up cost revising, connector marking, and basically, if you remember from my explanation of the solution graphs that we were looking at, the solve labeling, we label which of the nodes are solved and get to the solution. So, let us look at an example here. We have an S node which has a 1 connector to A and a 2 connector to B, C. Let us assume that the edge costs are 1 unit each. The graph is initialized to S. Now, after the graph is initialized to S, the question is, which hyper edge do I follow? So, we have alternatives of moving from S to A or moving along the path S to B, C. We start computing the cost. So, if I start at A, I add 1 edge cost to this. So, I will have 6, 5 plus 1, 6. If I take the 2 connector option, then I have 4 plus 6, 10 plus 2 because of the 2 connector, that gives me a value of 12. Given these two values, I will definitely follow the path S to A. Thereafter, I expand the node A, I get nodes B and E. Question is, how promising are they? So, I evaluate their age values, which is 5 and 5 here, and I revise the value for A now. So, I have 5 plus 5, 10, and this being a 2 connector, I have 2. So, I have a 12 here. The moment I have a 12 here for A, now this side would be 12 plus 1, 13 instead of 6. And now a little close examination will make you realize that this path no longer is promising for us. This has an estimate of 12 and it becomes more promising. So, I will rather follow that than going into expanding D or E further. So, let us say we then expand node C and get to 2 nodes F and G. The node F has a value of 4 and G has a value of 6. Once again, we will try to get to the estimate of 6 revised vis-a-vis the new values that I have for F and G. So, that would be 4 plus 6, 10 plus 2 because of the connector here, that would make it 12. So, I would have 12 here, and then I would have a revised value going up, 12 plus 4, 16 plus 2 because of the 2 connector, and that would be a value of 18. That is, when I have expanded the nodes of C, I have now an estimate of 18 for the solution that starts with the 2 connector from S. This makes me jump to the other side that I had already come up to A, and the search now comes this side. So, I look at evaluating node D and E and see how promising they are, and then back up their age values. So, this is the basic idea of the first portion of the algorithm, where we look for a top down partial graph exploration. We have the top down graph growing. So, we pick up the best available partial solution subgraph by tracing down mark connectors, and here I refer to mark as those connectors which indicate the current best partial solution from each node. One of the non-terminal leaf nodes of this best partial solution is expanded, and the cost is assigned to its successors. Now, let us look at the other portion of the algorithm, which is the bottom up cost revising solve labeling portion of the algorithm. So, we continue where we left from, that is, we are right now looking at this particular path, and we have node D and E. Let us say at this point we expand node E. Now, node E has 2 connector leading to H and I and a 1 connector leading to J. So, if you look at which way to follow at this point of time, you will realize that the cost of the 2 connector is 0 plus 0 plus 2, which is 2, and the cost of the 1 connector going to J is 10 plus 1, which is 11. So, this side it is 2 and this side it is 11. So, we will rather have this path. So, that is what is done, and in the algorithm. So, it follows this path, and once it follows that path, we realize that H and I are part of the solution set. So, we realize that, and before we mark them further, we revise the cost of the different nodes from which we have followed up to H and I. So, this H I cost, which is 2, makes the estimate of E being revised to 2. If the estimate of E is revised to 2, then 5 plus 2 7 plus 2 9, estimate of A would be revised to 9. Once estimate of A is revised to 9, 9 plus 1, the estimate at the top would be revised to 10. Once this revision is over, now we will look for solve labeling. So, we have H, which is part of the solution set, we have I, which is part of the solution set. Now, here I should point this out to you that I have marked the solved nodes in yellow color, so that I can see which node I am talking of as I am propagating it bottom up. So, H and I are solved. That would make node E as a solved node. Once I have solved E, now for the sake of this discussion and illustration here, let us assume that the subtree rooted at node D has been solved, and somehow I could mark D as solved. So, once I have marked D as solved, I can now mark A as solved, and once A is solved, because from S I have a 1 connector coming to A, therefore, I could mark S as solved. This is when I have the solution for the Andor graph that I started with. So, this is the second portion of the algorithm, the basic idea of bottom up cost revising, connector marking, solve labeling exercise. So, in this exercise, if a direction has all successors solved, then n is marked solved. Starting with the node that we have just now expanded, the procedure revises its cost using the newly computed cost of its successors and marks the outgoing connectors on the estimated best path to terminal nodes. And this is propagated upward in the graph. Now, having looked at these two ideas, I am in a position to formally put the AO star algorithm. One thing that I would love to point you out here is the following. We first initialize the graph to the start node, and if that is part of the terminal node, that means it is part of the solution set, then there is nothing to be done. I mark as solved. If it is not, then I am looking for top down partial solution graph, and then I am looking for a bottom up solve leveling exercise. And for this I keep on looking at this, I keep on looping until I can mark S as solved. So, in the first portion here, I pick up the best available partial solution graph by tracing down mark connectors. How do we mark them is coming from the next portion of the algorithm. Initially, to start with, I have no mark connectors and just follow one with the lowest cost. Later, I have the mark connectors and follow the path of the mark connectors. Now, this is where one needs to understand that unlike A star algorithm, where we also keep the estimate of the cost of coming to the current node, apart from the estimate of the cost of going from the node to the solution, the AO star algorithm only talks of keeping the promise of each node. This is because every time I am coming through the best possible way via the mark connectors. So, then we select the non-terminal leaf node of that particular partial solution graph and expand n. The next portion of the algorithm is that I start with looking at n and I mark the chosen connectors. The chosen connectors are those which have the minimum cost currently. So, once all successes through the connectors are solved, then I mark that particular M as solved. And once we reach up to S, as we have seen in our explanation of the AND/OR graphs, we will terminate the search. So, let us try to illustrate and trace the AO star algorithm in our particular example. So, on the right is the AND/OR graph that we have been looking at. Let us assume a couple of heuristic values to each of the nodes. So, we initialize and start with S, and we see that the price to the A via the 1 connector is 3, whereas the price to D and E would be 1 plus 1 plus 2, 4. So, instead of 4 or taking that path, we take the path from S to A. Next, we expand A to get B and C and once again compute the prices. So, here we have 4 plus 1. This is now revised to 5, and this side now cost becomes 5 plus 1, 6. Whereas, if you remember, we had computed the price via the 2 connector to be 4. Therefore, the search proceeds via the 2 connector starting at S. The next node that we expand is the node D. So, at D we have 2 options to do, one that takes us to node F and another that is a 2 connector taking us to G and H. The price that one has to pay for moving to F is 2 plus 1, 3. That is the price of this arc, and the price for the 2 connector is 0 plus 1 each for the connectors. So, 2 in total. So, the preferred path is what is marked here. This was the forward or the top down partial graph growing. Now, once we know that the nodes at this end are part of the solution node, that means I can mark D as solved because I have G and H which are part of a 2 connector and both of them are solved. So, D is solved for me. Once you have marked D solved, I can next look for expansion of node E. So, node E I expand, and this path that is marked has a cost of 1 which I follow. Once H is marked solved, I can mark E as solved, and once E is solved and D is solved, so I can mark my S solved. This gives me the solution to the end-OR graph, and I arrive at the solution of the given problem. So, we have looked at searching through end-OR graphs, and we have realized that end-OR graphs are represented through hypergraphs. End-OR graph searching is through an algorithm called the AO star, which uses some philosophy of the best first search, but somehow brings with it the ability to deal with the end arcs, and the AO star algorithm can be best looked at as 2 intertwined processes: top down graph growing process that arrives at partial solution graphs, and a bottom up cost revising, connector marking, solve labeling exercise that lets us move from the solution set to the parents one after another, marking them as solved until we reach the start node S and mark it as solved and arrive at the solution of the end-OR graph. The AO star algorithm that is used for searching end-OR graphs can be modified in a variety of ways to render it more practical. We can recompute a new estimated partial solution graph all at once. That is, rather than recompute a new estimated partial solution after every node expansion, we can expand one or more leaf nodes and some number of their descendants all at once, recompute an estimated best partial solution graph. Now, what would this lead to? Would some reduction in the overhead of frequent bottom up operations. The other modification could be what is called the stage search strategy. We should be able to identify few partial solution graphs having largest estimated costs. So, this we could keep on discarding periodically, but then doing this has a risk. The risk of discarding one that might turn out to be the top of an optimal solution graph. Having said that, the general AO star algorithm with its two operations, the top down and the bottom up intertwined, gives us the best optimal solution to an end-OR graph. In our next class, we will look at game trees and algorithms to do searching in game playing. Thank you very much.